Good morning, guys, or good afternoon, depending on when you're watching this video. Today we're going to be starting our piecewise functions unit, which is where the letters PF come from that you see there at the top of your notes. Piecewise functions, as the name kind of suggests, are made out of pieces of all the different graphs that we have learned about so far this year. So I really like this target. It offers us a way to go through all the different shapes and kind of combine them under one graph. And you'll see that in order to get things to be functions, we're going to need to adjust all the different pieces. We're going to need to cut them up so that they don't overlap. If you kind of remember, any graph that has multiple y values coming from a single x value, so like this example, it's not a function. And that kind of breaks some fundamental rules about how things should behave. If we started putting lots of graphs together, like a quadratic and maybe a square root graph, you'll see that that issue is going to happen as well. And so what we're going to end up doing is we're going to start cutting them apart so that one stops and the other starts. And they can be connected or they can be disconnected. They could have 2, 3, 4, 5 parts. But that's kind of a general summary and breakdown of what we're doing and where we're headed for this target. So let's go ahead and let's hop right into problem number 1 and 2. So we're going to graph two different shapes here on each coordinate plane. And then in a moment, we're going to glue them together underneath. So the first shape, you got to recognize it just has a variable x and a -2. And if you're dealing with just x, then that is going to be a line. Things that are important for lines will be slope and the y-intercept. So a couple of notes about the slope. That is the first part of your equation, the thing with x. And so the fact that it's got a negative means it's down 1 over 1. That again, slope is rise over run, kind of an important feature. The y-intercept is going to be the number that happens at the end. Because that moves you up or down, in this case down 2, the y-intercept has to naturally kind of be starting in that location. We move our line down 2, and then from there, we're going to follow a slope that is down 1 over 1, down 1 over 1. So there's my down 2, and here's my rise and run. And it would be good for us, down 1 over 1, down 1 over 1, down 1 over 1, to get as many nice points as possible. I'll say it that way. So this might take you a second. I definitely could put one more dot down there at the bottom. But once you get these nice points, going up 1, left 1 is the same negative falling slope. After we do that, we should be able to draw a straight line here through all of those locations. So if you have a ruler, or you could use the side of your calculator or a book, sometimes that makes it a little bit easier. But what's going to happen here in a minute is we're going to take that picture and we are going to cut it up along some location. And we'll either keep the left-hand side or we'll keep the right-hand side. So let's look at the second picture. Second picture, you should recognize this shape pretty quickly. That is a quadratic. So we can write that down. I know it's a quadratic because it's squared. And then in terms of transformations, we have a +2 inside of this group, and that is going to move this whole graph left 2. So the thing to remember about quadratics, their pattern is pretty important. 1a, 3a, 5a. It continues on. It's all the odd numbers. So 9a is the last one I wrote there. And the a value for this format happens in front of the parentheses. So there is a little 1 in the front. So all of these things are, maybe a little bit old. It's been a while since we've discussed them, but you're not allowed to forget, so you got to remember. So if a is 1, we're just going to get kind of those default 1, 3, 5, 7 odd unit spacings, and that continues on forever. So grabbing your pen here, we're going to go ahead and go left 2. We get to put our dot there. It does not have an up or a down transformation. And then we're going out on each side, and we go up this first distance right there. Then I go out 1 on each side, and I go up the next distance, which is 3. You can see my y-intercept here is 4. So this distance is taken care of. And now I need to go 5 away, which puts us at a total height of 9. Again, continuing out 1 box at a time, so that way it's a function. And that takes care of this. If I could, I would go 7 more, and that would land at a total height of 17. But now that I have the dots kind of laid out, we can do our best to draw a graph in there. Okay, so now that those are done, we're going to go ahead and we're going to combine them in our first piecewise function. So if we go down to the bottom of the page here, you can kind of see here in the left-hand side, we have P of X. This is one shape, but it's kind of interesting. This shape is made out of several other shapes. Okay, and the curly brackets kind of collect them all together into one location. What you have to do with these curly brackets is kind of read directly across and figure out what type of equations is it made out of. And then the last part here is the instructions on where to build them. This is going to be the new feature. This is where to limit each graph. And we haven't quite done this style of notation, but it should be a pretty easy notation to get used to. It uses inequality notation, so that's less than or equal to, greater than or equal to. And then sometimes we have combinations of those, and a compound inequality is what that would be. So basically what this does is it tells you where to cut each graph and piece them together. So for the first one, that is the line that we did right up above, and it's got the same y-intercept, it's got the same slope, but I need to build this line, if you look at the instructions, where x is less than or equal to -2. And so if I am less than or equal to -2, I would be to the left or on -2. That's where I need to cut this graph and paste it into my picture right here. So I'm going to try a little Photoshop trick. You guys will be stuck maybe copying that graph down again, but I'm going to take and I'm going to copy that picture down here. Okay, now because my graphs are different sizes, I got to rescale this. So hopefully this works. But as you can kind of see, once I'm moving it around, this is the same picture in the same spot as what was up above. Okay? So you guys have to do round 2 with that particular line. Now, in order to get this to meet the domain restrictions, this is a domain restriction that limits where our graph is allowed to be drawn, we're going to have to take and we're going to have to erase everything that doesn't meet that guideline. It's a bit like if you're building a house. You probably want your porch in a certain location. You want your kitchen in a certain location. You want your bathroom to be in a specific spot. Because if it's not laid out exactly like the plan state, you're going to have issues. You don't want your bathroom, out on the porch. That would be ridiculous and embarrassing. And so anyway, we don't want this graph to be drawn anywhere past -2. And so if I take my snipping tool, I can come here to -2 if you can see my cursor, and I'm going to pick everything that goes past that region and I'm going to delete it. It's gone. Okay? Nothing is allowed to live past -2. Now here's kind of the issue. Okay, if I get rid of that box, my end point right here at -2 itself, sometimes you're going to need a solid dot. Other times, you're going to need an open dot, which is something that we talked about when we discussed rational graphs. And it's all dependent on the type of symbol. So if you cannot equal -2 itself, you'll have an open dot to say that you can get really close to that location, but you're never going to quite equal that location. Okay, it would be a hole that you fall through. But in our case, we actually want it to be closed because we can equal -2 itself. And so that dot is a solid dot that we could stand on because we can equal that x value. Now we're going to do the same idea, but we're going to do the same idea with this secondary equation and its restriction. Keep in mind, this is allowed to live greater than -2. And so that's to the right. All of those x values are greater. So like 1 is greater, 4 is greater, 5 is greater, 5.5. Those are all greater x values and would satisfy that inequality. So I'm going to go ahead. I'm going to take my graph from up above. I'm going to copy it. Oh no. And it needs to be the exact same graph. And you're going to notice here in a second that we have kind of some issues. There we go. That makes it a little bit better. So this might take a second for everybody. Essentially, you're doing the same graph twice. I'm just being fancy. There we go. So we'll lock that in. You'll notice the moment that I put it on at the current image, it is not a function. So we have kind of some points over here and even in the middle, anywhere along that strip of the graph where there are lots of y values coming from one particular x value, and that's not ideal, and that's because we have not limited the quadratic shape yet. So what we're going to do is we're going to take anything that's less than -2, and we're going to cut that away. So my box goes all the way up to -2. I'm going to delete that. And then we have kind of an interesting predicament. The point where they both meet, if I turn this off and then on, okay, you can see that there's already a solid dot there. If I have another solid dot there, then it's not a function because you have a dot on top of a dot. And so what you're going to need to do, because it is greater than, it's not actually equal to, so that might be a note worth making. It's not on -2. We need to make that particular end location into an open circle. So this might be helpful if I reshade it. And if you have colored pencils or markers, perhaps for the next set of problems, you could reshade or color different areas of your graph as well. But the end marker that I'm going to need is a solid dot that has been hollowed out. And what you're going to notice here, if I get this correct, is that the two fit together like puzzle pieces. I didn't do the best job, so maybe I can come back to the earlier graph and make that a little bit smaller. Okay. There we go. And if I zoom in, okay, this is kind of what's nice about Photoshop, is now you get an inside view of what's happening. So the original line extends from this point onwards to the left, so left of -2, smaller than -2. But then the right graph picks up directly here, and it goes over to the right, and it's that nice light pink or purple open circle. But they fit together like this hooking together, and that's called something special. If you don't have any breaks in your graph, that is considered to be continuous because it continues on without you picking your pencil up off of the page, I suppose. Graphs that are piecewise don't have to be continuous. They can be discontinuous, where they have jumps or gaps or things along those lines. But we typically like continuous graphs. They play a little bit better with some other math. So let's go ahead and let's talk about the overall domain. At the top, if you talked about the overall domain, this has x values that go left and right forever, so all real numbers. Again, that's negative infinity to infinity. And then the bottom is the same idea, or the y values, I should say, goes down to the bottom and up to the top forever, so negative infinity to infinity. For the quadratic graph, okay, you can see it there. The x values, don't know why I started with range, but the domain and the x values go left and right forever. It's a very common thing for the graphs that we have done for the most part. And then the y values is not all reals, but from 0 to infinity. None of the y values are going to be below the x-axis. That is just not something that happens. So the piecewise graph is kind of a mix-up, mash-up of those ideas. You really kind of need to look at this end result to know what your domain and range is. But the domain, because these fit together and there's not a gap, and because our instructions butt up against each other right here, is that it goes from negative infinity to infinity. That is all reals. The y values actually kind of have that feature where nothing escapes or gets below the x-axis. And so we're going to go ahead and put 0 to infinity. And you just got to be careful. Because we are using open circles, sometimes that might be a parenthesis if the lowest point is an open circle, and other times that might be a closed bracket if that lowest point is a solid dot. And that is what's happening there at our lowest point. We have a open circle, but then it's filled in with a closed circle, a solid dot. So we can equal and stand at a height of 0. All right. So, couple of interesting thoughts about piecewise graphs. Open points happen again. We talked about those when we talked about holes in the rational chapter. You can have holes when factors or things like that cancel out in the numerator and the denominator. So open holes happen if it's less than or greater than, if they're not equal. They're made out of pieces, and those pieces can connect, or they can be separate. If you have any other thoughts that you want to put in that area, go for it. You can do anything you kind of want in that little zone. It's all for you. And then the bottom, just talking about whether those things connect or disconnect. That's what continuous and discontinuous mean. These two shapes are set up in a way that they are continuous. You don't need to pick up your pencil. Okay? Pencil stays down the whole time you trace the graph. All right, just so you can maybe see that in action. If I start graphing here on the top left as early as I can trace along this shape, and I never have to pick my pencil up to go from shape to shape across the whole thing. It would be an infinite pencil and an infinite drawing. Okay, so that is our first page, and that is our introduction to piecewise functions. And I hope that kind of makes sense because we're going to build off of it. It really is like a construction theme. We got to go ahead and we got to follow the blueprints. We got to make sure that everything's getting built first off as the proper shape, and secondly in the proper location. So if we look at problem number 2 here on the next page, we're going to be building a square root. It's got a square root sign. Square roots, remember, are one-armed graphs. And so they have a pattern of 1, 3, 5, 7, 9, just odd numbers. But they work by stepping up whatever this a value is. And so this has been reflected. So I'll try to jot as much down as I can. Reflection. And then it doesn't look like we have anything else really going on. So if I were to graph this out with dots, okay, and maybe graphing the whole thing is what you do first in these cases. So start at the center, the origin, since we haven't moved, down 1 and over 1, down 1 and over 3, down 1 and over 5, down 1 and over 7, if I could. But we're going to have to go ahead. We're going to connect these into that one arm. This is not so much an aerobics arm, as I kind of made that joke. It is more of a bowling arm. It goes down and over. There we go. Trying to get it so it goes through those dots, and we'll put an arrow on the end. Okay. Now, the second shape, if I underline it here, that is a line. One thing to maybe mention, we should probably do this first, I guess, is that square root needs to get built at a certain location. So it needs to get built less than 4, so that's left of 4, and it cannot actually be built on 4. We cannot equal 4. So everything that we graphed that went prior is good, but everything that comes after 4 is bad. So I'm going to erase all of that. We don't really want it there. And then this last point actually is also bad because it's on the boundary line. And if you're not allowed to build something on a boundary, you better make sure that it gets hollowed out. So I'm going to put a solid point there, but then I'm going to erase the center of it. So that way it is an open circle. We may connect in there, we may not. If you have a garage that's connected to your house, then that's kind of like the connection we made earlier. But some people have garages that are not connected, and so there's a disconnect between those two things. It just depends on the other shape, you know? So if we go to that other shape, all right, back up here, this other guy is a line. Get back on my pen. Okay. So that line has a slope that is 1 over 1. There's a 1 in front of the x. And then we also need to go down 6 because that's what minus 6 does. It's the y-intercept. A couple of notes about where we need to be building. We need to be building to the right. Oops. Greater than 4. And we can actually be on 4. So a couple of notes about where. If we go ahead and start to plot out those points, I would always do this kind of tentatively. This is kind of like if you were on a construction site and you saw those little flags. Those flags are there to mark some things down. So if we go down 6, okay, we probably don't want to put an official dot there because, again, this is outside of that building zone. We need to build greater than or on 4. So I'm going to go ahead. Let's shade this down for a second. This is tentative. The next dot would be up 1 and over 1, and I am not allowed to build here yet. So let's keep following that path. Up 1 and over 1. This is still not meeting that requirement. Up 1 and over 1. And then the moment I go up 1 and over 1, we should be asking ourselves, can I build here? And the answer is yes. So I'm going to shrink that down so it fits just inside of that open circle. That, again, doesn't have to happen, but it's nice when it does. Okay, so we can see that location. And now we continue with that up and over, up and over, up and over, up and over, up and over slope. Okay, when we piece these two things together, we get kind of an interesting shape. It curves down for a minute, and then it's going to start here in this central dot and go up and to the right at a straight constant pace. So while you're doing that, it might be worthwhile to erase the points that really shouldn't be there. So we put some flags down so we knew where it was headed, but now we're going to pull the flags back up because, you know, they don't need to be there. Okay, and so this is our final piecewise graph. It's got the square root coming in and the line going out. So let's talk about its domain and range. This is just good to do as practice. The domain here, or the x values, go from 0 to infinity. 0 would be a bracket because that's where it starts and it's equal. You can take the square root of 0 and that's not a problem. The range, if we talk about the range and the y values, the lowest point is down here at -2. That's the lowest height, I should say. But because it's an open circle filled in by a closed point, I can actually stand at that height, and that will be a height that is achievable. Now the question that they actually ask is this continuous or discontinuous? And so kind of that same idea from earlier, that if you take your pencil and you start graphing, so once you start you have to keep your pencil down. I am going to be able to trace over that whole shape without lifting my pencil whatsoever. Okay, so this is a continuous graph. All right, discontinuous graphs have discontinuities, so jumps or gaps or things like that. And actually in calculus, you'll talk about some other types of discontinuities that occur with some pretty hard ideas, but this is the start of you thinking like that. So let's go ahead and let's do the next problem. I think this will kind of get us rolling on some of the more complex cases. Problem number 3 says write the equation for the piecewise function t of x. So this already has a name. We don't get to name it, but it's going to be t of x, and we need to equal. Remember, we've been using those curly brackets to kind of hold all the pieces together. It's like glue. And if you kind of look, this is an interesting shape. If we were building a house, this would be like a abstract house. We have kind of a shape over here on the left of -1. It seems to me like this might be a quadratic. Just looking at the spacing, you got to be careful because sometimes you can chop cubics in half and they still look kind of quadratic-y if you keep one half or the other. But the spacing is 0.5, 1.5, 2.5, that would be 3.5. And so if you think about what's happening, you're taking 1/2 as your a value, so half of 1 and half of 3 and half of 5 and half of 7 compresses it down. And so that might not be the most logical thing right off the gate, but those spacings behave in that way, so we know it's got to be a squared, x squared type of a situation. Now after that, so -1, we kind of travel upwards, we flatten out, and then we start speeding up again. That takes a dramatic shift after 1 itself. So my line's a little bit off, but between -1 and +1, we have a cubic shape. So remember, cubics are those squiggles. They look like this, and basically we just cut it and cut it so that we're keeping the central part of the cubic. That cubic appears to have been stretched out. The a value is equal to 2. Remember, it would be 1a, 7a, and then 19a. And so we're really just kind of keeping that central starting spacing. Okay, after that cubic, we have a line. It is a constant, which is worth noting. Constants are just y equals a number. And in this case, since all the heights are 2 and 2 and 2, it's going to be the equation y equals 2. All right. For the cubic, if I wanted to write that out, it would be 2 and then you have x. We aren't moving away from the origin, and so we would close the parentheses and just put cubed. And then here for the quadratic, it would be y equals 1/2. And this quadratic, I think, has moved around a little bit. The vertex is sitting down over here, so that moves us left 1. So remember, left 1 is plus 1. We need a squared to actually make it the quadratic shape. And then down 2. What you are going to need to do here in a second is take those equations that we just worked on, right there, and here, and even right there, and you're going to need to write them as our 3 separate equations for t of x. Okay, so these lines are where the equations will go ultimately, and it doesn't matter which order, but typically I go from left to right. That seems to make the most sense. So the first one, if we go ahead and copy down 1/2 x plus 1 squared, and then minus 2. The instructions, if you've kind of noticed, will always follow a comma. So I just put a little comma there. And now we need to go ahead and say that we're building to the left of -1. So that's x is less than -1. And what's kind of unique about these questions in particular is you get to choose. It is very hard to tell which shape has the open circle or which shape has the closed circle. And so you kind of get to make that call. What you're not allowed to do is put an equal to here, and then on the next shape also put an equal to, because that would stack a dot on top of a dot in that location. And again, that's not a function. So if you wanted to make that one a closed circle, you'd put an equal to underneath. If you want to keep this one open, then don't put the equal to, because you cannot stand on that location. Let's go to the middle shape. So I'll change colors a little bit. That would be the 2 and then x cubed equation. Because this starts and stops, we're going to have to craft what's called a compound inequality. Where does it start? It starts at -1. Where does it finish? It finishes at +1. Okay, so you just have this boundary of clipping everything outside of that range. And then the x values that you're graphing are the x values that are between them. So remember, we did not close in that circle. That means that needs to happen here. And then we get to make the call for what's happening over in this location. Okay, right there, we can say x is less than 1, which means that our cubic finishes with an open circle, or we can make it closed, and so it has a closed bottom end and a closed top end, and the other pieces fit around that. Totally up to you. My answer key might be a little different than what you guys decide in class or what I decide here on the video, and that's okay. They just need to fit together like those puzzle pieces I described earlier. So I'm going to make it open on one side, and then I'm going to go back and finish out this last constant. So it's just the equation of 2. Remember, this says y equals 2, and that matches what we wrote. I'll need my comma, and then we are going to extend further over from 1. So that is, you can say this a couple ways, but I like putting a 1 and then having x be bigger than that. So this is, again, greater because it's on the eating end of that inequality. If you chose to write this the other way around, okay, you could write x is greater than 1. That's fine with me because they're both the same idea. Okay, but no matter which way you do it, you're going to have to make sure that you get that equal to in there, because if this is open, we need to have that be closed so that they complement each other and fit together like they should. All right, so that had a lot of talking on it. I hope that made sense. Gradually what we're going to do is we're going to have lots of pieces all working together. And so that's a pretty high-level concept. If we go ahead and try our last problem probably for today, we have 3 different equations. and we're going to go ahead and graph the first equation to the left of -1. Okay, so that's everything up here. If you were looking at what shape that is, it's a line, and the slope is down 1 over 1. The y-intercept is 0. And we need to build that to the left of -1. Okay, so if you are somebody who needs a little bit of a reminder, maybe put an arrow here, and that's going to be our split, and we're going to keep this half of that arrow. That's going to be the good half. So some tentative dots. Again, these are like flags. So I'm going to come down. Oops, sorry. I don't go down. I start at the origin. I'm not really allowed to build there, since that is against the rules. Now my slope does say down 1 and over 1, but if I keep building in this direction, I'm not getting any closer to the direction I actually need to be building on. So let's not keep building that way. Let's maybe go up and back 1. Up 1 and left 1 is still that same negative falling slope. And now that I've graphed a couple of these points, I can see that I'm in the right location, which is good. You don't want to build in the wrong location and then keep the wrong half or anything like that. So just putting a bunch of dots out here. Let's go back to our instructions. We are not allowed to build on -1, so even this dot itself is going to get erased. Okay, I'll need to put an open circle there in a second. So let me go ahead and let me draw my line from here to there. We'll put our arrow on the end. That's important. And then just so I can have a nice circle, open circle, I'm going to make that kind of big and then hollow out the center. There we go. So that's the line all taken care of. If you were watching the construction workers, you'd be pretty happy with that. The next shape, if I go ahead and look at that, this has one of those compound inequalities. This means we're going to be building between two different locations. So a couple of notes that we could make. It is a quadratic. A is equal to -1. And then you got to be extra careful. Sometimes those instructions get mixed in with the equation. So that -1 is part of the instructions. It's not part of the equation of moving it down 1. So that just means we have to build between -1 and 2. Anytime you see an x in the middle, you're building between two numbers, the smaller number and the bigger number. So if I go ahead and if I graph this, let me put different color here in the center. So x squared starts in the center. And then I go over 1, down 1, since the a value is -1, over 1 and down 1. Then I get to go over 1 and down 3, over 1 and down 5. But if you were kind of paying attention to those instructions, which it's hard to when you're first beginning, I didn't go further left than -1 because that's the left boundary. I actually ended up going past +2. So that last dot isn't something that I want to keep around. Okay. Now the endpoints are closed and closed because I can equal -1 and -2. So I don't need to erase the middle and make an open circle, but I do need to connect these dots in a quadratic shape. Oops, that is my eraser. Let's get back on the pen. All right, so we have a quadratic U. It's been flipped upside down, and we cut it so it only stays between -1 and +2. Now I got to go ahead, and we're going to get this last shape in here. The last shape, if you look, is a line. Lots of lines. So you got to remember slope and how slope works. Slope is up 1 over 2, and the y-intercept is down 6, -6. And so this is going to be something where we're going to have some temporary dots. So if I travel down 6, can't really put a dot here. I'll erase it in a minute. Up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. Those all look great to me. I'm not going to connect this last dot because he gets thrown into the garbage bin. But we are going to go ahead and connect the dots that matter. And we might have to kind of consider, is that final dot there at the end, that endpoint dot, open or closed? So looking at our instructions, it says x is greater than 2. So I need to go in and I need to hollow that location out. Again, if I have a dot above a dot at the moment, this is actually not a function. So right in that location, I had 2 dots, which is against the rules. Okay, now that it's hollow, if I were testing it, it would go through that and then hit the solid point that's above it. Or same thing here. It would go through that open hole and hit this solid dot underneath. So the question that they're asking at the bottom, is this continuous or discontinuous? This is a graph where we have some discontinuities. You can see that there's a gap in its heights. And you can have gaps in heights. You can have gaps in horizontal movement. They're just disconnected from each other, which is where the word discontinuous comes from. All right, guys. Hopefully this video helped. We will finish up the notes tomorrow. But in the meantime, if you have extra class time, let's try to maybe start on the homework and see how you guys are taking these problems apart and maybe laying down the foundations to our early piecewise knowledge. I'll be back tomorrow, and I should be able to answer some questions. So thanks, guys. I hope you have a terrific night. We'll see you later.